lot of you here. I guess you must all like public confessions. It's kind of intimidating. I'd rather be doing this one-on-one than in front of so many people. I guess I just have to remind myself of the American proverb, the more you confess, the more books you will sell. Anyway, you all have one of these clickers hanging around your neck, and there's always a danger in starting a talk about education with technology. I love technology. You'll find all the latest gadgets in my pocket, but I don't believe that technology is the magic bullet in education. We should really be focusing on pedagogy, not on technology. But we'll be using this first simply as a polling tool, but later on I'll show you how you can actually use that as a pedagogical tool. But I want to say right from the start that the focus is not on technology, it's on pedagogy. So since I have to confess in front of you, let me start with the very first confession. When I started teaching at Harvard 27 years ago, I never asked myself the question, how am I going to teach? It's kind of strange, right? Because when you start something new in your career or in life, the first question you should really ask yourself is, how am I going to do it? The question did not even come up in my mind. It was perfectly clear what I was going to do. I was going to do to my students what my professors had done to me. Lecturing. In fact, I did that unconsciously even. I sort of naively believed that I had learned physics by sitting in a classroom not very different from this one, listening to my professors present. Now, when I became an assistant professor at Harvard, my colleagues asked me to teach a course that no one wanted to teach. Physics for pre-medical students. These were not students who wanted to learn physics. They had to learn physics in order to get into medical school. And, most of my colleagues would come close to committing suicide at the end of the term when they saw the results of the student evaluations. But, even though I started mimicking my own teachers and lectured, the same way probably many other physicists lectured pre-meds before, the signs that I was receiving were actually very positive. I very quickly got positive feedback. Right? One of the metrics is the student evaluation questionnaire. I already told you most of my colleagues did not get high evaluations, but I got 4.5 on a 5-point scale. Clearly the students liked what I was doing in front of them. Also, I could give these students some really tough problems on their exams, problems I wasn't sure I would do well on under the pressure of an exam. So in short, they did well on what I considered complicated exam problems. They liked me as an instructor. Obviously, I was doing the right thing. And that illusion of being a good teacher went on for many, many, many years. In spite of the fact that there were continuously reminders that something was wrong. For example, on the student evaluations, every year, a number of students would write in the comment section at the bottom, physics is boring, or physics sucks. I could never make any sense of it. I mean, what is more interesting than understanding how the universe around us works, right? So I just ignored those remarks, especially... Or, when I go to a party and people ask me what I do for a living and I tell them I'm a physicist, I get these worried looks. Oh, physics. I had such a hard time with physics in high school or in college. Or my dentist who recently, and I couldn't even talk back because I had the thing in my mouth, right? Said, you're a physicist. I got an A for physics in college, but I really didn't understand anything. It always makes me feel very uncomfortable. I never understand. I tend to be a positive thinker, so if I have positive signs and negative signs, I ignore the negative ones and focus on the positive ones. So for many, many years, in spite of all of these signs, I happily lectured, believing that I was a really good teacher. I'll show you later how that dream unraveled, or how that illusion, I should say, unraveled. Anyway, since we have that technology around our neck, let's try, because I think in order to have a meaningful discussion about teaching, we should really first reflect on learning. So I want to put you to work with a little exercise, and we're going to use the clickers for that. So let me explain to you how they work. They have no on-off button. They're always on. Only the last click counts. So I'm going to ask you a multiple choice question, and if you press 2 and then you think, oh no, I should have pressed 3, you can press 3. The 3 erases the 2. You only get to, you can click as many times as you want, but you only get 1 vote. So the system remembers what you clicked before and erases that choice. The display will show you a recorded answer. Just stay away from the channel button. If you accidentally press on the channel button, just wait until the little light flashes. The channel, it should say, here it says 41, but on your clicker it should say 55. Okay, so let me show you what I see as an instructor. I have this little window, this little thing that already 41 of you have been playing with your clicker. I haven't even asked anything. At any point in time, I can click on this button, and I see a distribution of the different clicks. Now, why don't you go ahead and all press 1 and look at what happens to this. Very good. I love it when audiences follow my instructions. Notice how the distribution changes instantly to reflect the new distribution, right? And if you were to all press 5 now, but I'm going to stop this here to prevent you from playing with your clicker, you would see the distribution change to only 5s. I've stopped the polling right now, and you can see that 130 people have answered. If you press now, you'll see a circle with a line in it, meaning the polling is not open. So that's really all there is to the clickers, which is good because you don't want to be struggling with technology when you're in the classroom. It's extremely simple. Actually, there's one more thing. When I press the stop button, which I did just a moment ago, the software captures a picture of the screen, what was on the screen behind it. So tonight, if I want to review the data, I can see that distribution that I captured together with a picture of the screen. So regardless of what presentation software you use, this is just a PDF file in Acrobat. You keep the question. It could be a Word document, PowerPoint, whatever you want. Okay, turn the clicker around for a second and look at the back. There is this barcode. Each clicker has a unique ID number. So you think you may be anonymous. No, we know exactly who you are. Just kidding. we didn't record the ID numbers. But in the classroom, you could actually track if you want individual students. You could have the students submit their ID number together with their email to a website, and then you can get a nice spreadsheet that tells you exactly what each student does. Some faculty use that for credit. I think that's a very bad idea. You want this to be formative assessment. You want this to be an opportunity for students to take risk and try out things without being worried about points, right? If you give students points, they'll do whatever is necessary to earn the points. We don't want students just to get points. We want them to learn. And the two, unfortunately, are not compatible, right? Think about how many students actually study not in order to learn. They study in order to pass the test. In an ideal world, those two things should, of course, be the same. But we live in a world that's far from ideal. So you give points for clickers, and students are going to do whatever they need in order to earn the points. I urge you, if you're a tweeter, do a search on Twitter for the words clicker and class. It's hilarious because you'll see how students perceive clickers from their perspective. You'll see students post pictures of being in the classroom with 5 clickers, 4 for their for friends who are not coming to class, and 1 for themselves. Why? Not because they want to learn for the people who are not there. No, because they want to get the points for the people who are not there. Anyway, so let's get to work here. Put your clicker away for a moment and grab a little piece of paper. I'm going to have you write down something very personal on that piece of paper, so make sure that your neighbor can't look over your shoulder. You could also take your smartphone or your computer, it doesn't matter. Incidentally, if you want to know more about the clickers, you can either contact the people in the Center for Teaching and Learning staff, the staff at the Center for Teaching and Learning, or you can go to this website from Turning Technologies. That's at the bottom of the screen. And I know this screen is really low, but you can see it on the side screens too. Okay, on that little piece of paper, I want you to write down something, some skill or some knowledge, something you are really, really good at. It could be public speaking. It could be solving partial differential equations. It could be interpreting medieval works of art. It could be diagnosing diseases. It could be baking cakes or gardening. Something you're proud of, something you do well, something other people respect you for. And ideally, I want what you write down to be something that has been important in your career. So unless you're a baker or a gardener, I don't think you'll write down probably baking cakes. Okay, so once you've written that down, fold up the little piece of paper so that nobody can see it. It's just personal information. And you're all successful individuals, so it shouldn't take that long. Usually when I do this in an academic environment, some people raise their hand and say, only one thing? Yeah, only one thing. Do people need more time? Anybody? Good. Okay. So now I had you commit to this because I want to ask you another much more important question. And that question will cause you to think a little bit harder. Because now I want you to think about how you became good at whatever it is that you wrote down. What were the circumstances that led you to develop this skill or this knowledge or whatever it was? I can see it once from your faces. The problem is when we're good at something, we enjoy it. And when we enjoy it, we learn without really being aware of it. So anyway, write down a few words describing how you became good at it. Incidentally, I've done this little exercise all over the globe. At some point, I'm just going to publish the data that I've collected so thank you for participating in the study. But I should probably get IRB approval for this. Anyway, so I've done it all over the globe. I've done it in Latin America, from Chile to Colombia. I've done it all over Europe. I've done it in Asia, in South Korea, Japan, China, Taiwan. I've done it in Africa. I've done it all over the North America, and it's amazing. There are no cultural differences if you look at the answers to the second question. It's amazing. And actually, that's not that surprising. I say it's amazing, but it's not that surprising because we're all human beings, and our brains are all wired to learn the same way. There might be cultural differences, but there are no biological differences in the wiring of the brain and in the way we learn. So I've collected the answers to the second question, and they typically fall into the following 4 categories. I learned it by trial and error. Doing it and then making mistakes and then, trying it again. I learned it by listening to lectures. I know the screen only says lectures, but I have to add the word listening there because giving a lecture is very different from listening to a lecture. So I don't want there to be a misunderstanding here. I've learned it by practicing. I've learned it by apprenticeship, by tagging along with somebody who's really an expert and looking over his or her shoulders and then mimicking that person. And then there's a mishmash of other categories like friends and family and so on. I would like you to select the choice that, and I'm going to open the polling now, that comes closest to what you wrote down as the answer to that second question. So please select whatever comes close, and let's see if Charlotte, North Carolina is any different from China or Chile or Colombia. Okay, so we have 125 people. Are you ready? There we go, 130. And no, it's exactly the same as anywhere in the world. The most popular choice is practice. Typically, I get between 50% and 70% for practicing. We learn by doing. We learn by practicing. Now, that's not why I did this little exercise. I did it because there's something else really interesting about this distribution behind me. What is that? Lectures. Only 2%, only 2 people in this audience. I pity you, I'm sorry. Learned by listening to lectures, right? But the majority did not. Now, that's kind of strange right off the bat, because how do we teach? This is how we teach. All around the globe. This is a picture actually of me teaching. I don't want to put anybody else on the spot. It's a very old picture. This was taken BC, before computers. See, I'm using an overhead projector there. Anyway, so we see right off the bat that there's something kind of interesting happening here, right? You just admitted that this skill that was important in your career, in your life, you did not learn it in lectures. So here's what I would like to do today. I would like to first talk a little bit about education. The outline is at the bottom of my screen, so the screen is very low. So if you wonder what I'm pointing at, you can see it on the side screen. So we'll talk a little about education. What is education? What do we mean by it? I mean, we're educators. We all sort of know what is education, but if I were to ask you to take that little piece of paper again and write down a concise definition of the word education, I'm sure that many of you would be struggling, including myself. We know what we mean, but to articulate it is not that easy. So I want to think about that a little bit more, because after all, as educator, we should know what education means. Then I'll talk about peer instruction, which you heard Valerie mention, which is a technique to engage students in large classrooms, which I developed after discovering that in spite of these good indicators, my students were not learning anything of value in my class. Shocking. I'll show you the data. And at the end, since we're in an academic environment, I'm sorry, but there'll be a test. So you better pay attention. Huh? Okay, so let's start with education. And let's ask ourselves the following question. What is it that happens in a lecture? Here's a lecture, right? Ironically, I'm giving you a lecture about bashing the lecture. So let's ask ourselves the question, what is it that happens in a lecture? Take that picture of me teaching here. I would like you to describe the process on the screen behind me with 1 or 2 words. And ideally, I want one of those words to be a verb. And there are 2 verbs I do not want to hear: teaching and learning. So you have to find another way. Go ahead. Passive, pointing, performing, imparting. Go ahead. Sharing, sleeping. Did somebody say sleeping? I just told you this was my class. But now that you mentioned sleeping, that theme will actually come back in my talk twice. First of all, I recently came across a fantastic quote. Some people talk in their sleep. Lecturers talk while other people are sleeping. I'll show you some absolutely stunning data from the MIT Media Lab that actually will reinforce that point in a pretty incredible way at the end of my talk. And there might actually be more truth in that statement that you just saw than you may think. But no, these are my students. They're not sleeping. So, okay. So we heard lots of things. We had some verbs that refer to me, pointing, talking, and so on, and others that refer to the students, verbs and other words like passive or, listening and so on. But I would like the whole process. What is it that is happening? Something that involves both me and the students. Yes?
Transmission of information.
You must have heard my talk before. Transmission of information. Sometimes people say transmission of knowledge, but I don't know what knowledge is, right? Lectures focus on the transmission of information. And you know what? My students had rubbed that in my face very early in my teaching career, and I had ignored it. I just told you that when I started teaching, I did not ask myself what I was going to do. But there was a question that did come up in my mind. What do you think it was? Not the how, sorry. The what, right? I asked, what book am I going to use? So I went to a colleague who had taught the course before, and I said, what book should I use? And he said, oh, in this course, we use Halliday and Resnick. I can see a lot of people shake. Yes, it's been a classic for 30-some years, and it's still being used. Anyway, I was educated in Europe, as you heard, but I was told that in the US, students buy the textbook. In Europe, we would never buy the textbook. Why buy the textbook if the professor is presenting the book to you? But anyway, I was told you have to make sure that the bookstore has enough books in stock. So I walked to the Harvard Coop. Those of you who have been in Harvard Square may know that store. And I said, be sure that on September 15th, you have 150 copies of Halliday and Resnick. And as I walked back to my office, I said, wait a minute. If they have the book and I have the book, what do I do in class? So I stopped at my colleague's office, knocked on his door, and I asked him that question. And he said, oh, don't worry. There are lots of different physics textbooks. And he had a whole shelf full. And I started looking, and I found the perfect book. It was perfect for two reasons. One, it had a different approach from Halliday and Resnick, so I was not just regurgitating the content of the book that they had bought. But that was not the important reason. The important reason was the book was out of print. Students couldn't get a copy of that book. So for each class, I spent, 10 hours preparing my lecture notes. And then in class, I would either project the lecture notes, here you see it, I would project the lecture notes on the overhead projector, or I would write them on the board behind me. And because the lecture notes were different from the textbook, I decided I would give the students a copy of my lecture notes. So at the end of class, they could just grab a copy and go home. Now, why do you think that I hand them out at the end of class? Isn't that already admitting that there's a problem? Why force the students to get the words out of my mouth if they could get it from my lecture notes? Anyway, that never came up. But you know what happened? The unexpected thing that happened was that at the end of the semester, about half a dozen students wrote in their comment section on the evaluation, Professor Mazur lectures straight from his lecture notes. Hello? I mean, what was I supposed to do? Develop another set of lecture notes to lecture from that was different from the lecture notes I handed out to them? I was livid. But the students had a point. I was lecturing from my lecture notes, and if they'd read the book, they would have seen that it was not that different from my lecture notes. Now, given the fact that 99.9% of all classes around the world are taught this way, we could ask ourselves the question, is that what education is? Is education, as you correctly said, I may not agree with the statement that that is education, but is what happens in the classroom, the transmission of information, does that correspond to education? So let's actually, I hadn't planned on doing that, but we could do a quick poll. So if you believe that education is just the transfer of information, press 1. If you think that education is more than just the transfer of information, press 2. Let's see where we stand on this issue. So if education is just the transfer of information, as you see on the screen here, press 1. If you think education is more, press 2. Okay, so let's see what we have here. That's the same 2%, there. So I'm glad that most of us agree that education is more than just a transfer of information. Let's first talk about that 2% there. The two people here who apparently learned from lectures. I'd be surprised. I'm going to look at the data, slice the data tonight, and see if it's the same two people. So, to those two people, I have bad news for you. You are risking of losing your job. Because if education was just the transfer of information, then what would be the logical thing to do? Replace it with a robot, but we can't build that. Put it on the web, exactly. Just film the best possible teacher for every subject, you know, in different languages. You may need to refresh it every few years because, you know, clothing gets out of date. But what would you lose by doing that? What would you lose by doing that? Interaction. But how much interaction is there in the classroom, right? Step into a random classroom, sit in the back, and look at the lack of interaction. Somebody mentioned before here in the front, passive, when seeing that picture. Most students are totally passive. I'm working very hard on interacting with you, but in a typical class, there's hardly any interaction. What would you gain by putting, yes?
Well, I always wonder, I mean, like, isn't there something to be learned from students learning how to listen to lectures and learning how to take notes? I mean, isn't that an important skill? And I always wonder if you do, you know, these flip classes and you put, you know, the listening or the transfer of information on the web, do they actually learn that skill?
So is there any value in listening to a lecture and taking notes? And maybe that by putting it online, you would lose that skill. But I'm going to show you some data that's pretty convincing from this MIT Media Lab. I'm dying to show it to you because it's going to be a revelation to you. But I would argue, even in the absence of those data, I would argue that when you watch a lecture online, you could also take notes and listen. There's the same activity there, right? The only thing you can't do is you raise your hand and ask a question to the instructor. Well, you could in a forum post a question and have an answer that comes later. You cannot have the instant feedback, but there's very little of that happening in a classroom. There's another benefit from putting it online, which you cannot have in the classroom. Have you ever had a student in your class raise her hand and say, "Professor, could you please be quiet for 5 minutes? I need to think." Never happened in my class. But online, you can do that. Or if you read a book, you can do it. You can put the book down and think, In a lecture, when you're listening, your mind is held captive by the presenter. We're very poor multitaskers, right? If your mind starts wandering, you're no longer listening to what the person is saying. But online, you could actually pause it and think. Or you could do something else. Have you had a student raise his hand and say, "Professor, could you please repeat the last 10 minutes? I need to hear it again." Right? Online, it's very easy. Or you could stop the playback and call up your friend and say, "Hey, do you understand what Professor Mazur says 8 minutes and 21 seconds into the tape?" Right? So I think you would gain actually a lot without losing too much. Yes, you will lose interaction. I totally agree. But there is no interaction in the first place. Fortunately, 98% agrees that we will keep our jobs because there is more to education than just the transfer of information. But now I'm going to pick on these 98%. What is it that is missing in this picture? What is it that education is more than just the transfer of information? Come on, you selected two. Practice, very good. Exactly, the exercise we did at the beginning. You have to do something. As a learner, you need to do something with that information. It's not just opening your skull, putting the information in, closing your skull. No. You have to be able to take this information and extract from it the models, the knowledge, the expertise that allows you to apply this knowledge into a new context. So much of education is simply instructors delivering information to the students. Then you wait 2 months. You isolate the students from each other, from any source of information, put them in front of a piece of paper, and you have them regurgitate the same information back to you. I was educated in Europe. We pride ourselves in good education in Europe. Well, I must admit, I've probably forgotten 99% or 99.9% of everything I've ever learned. In fact, the psychologist Skinner once said, education is what is left after all that is learned is forgotten. You're laughing about it, but there's actually quite a bit of truth in that. You know, in 1660-something, I forgot, the Dutch defeated the British in the River Thames. I remember that we discussed that at one point in our classroom in Holland. And then on the exam, but I forgot the year, I'm sorry. Maybe somebody can Google it for me. And then on the exam, in what year did the Dutch defeat the British in the River Thames? And I apparently must have written down enough correct answers to get my high school diploma and go to the university. But did I learn something of value? It would have been much more interesting to understand why the Dutch were able to defeat the British right outside London in their home turf on the River Thames. Anyway, but I think actually a lot of education is just that. Students parroting back the information or parroting back procedures. Not that long ago, I was at the University South of Boston, quite well-known university, and I gave a talk in the physics department, and after my talk, which was on education, one of the instructors came to me and said, I had something really strange happen in my classroom this year. He had worked really hard on bringing physics to life for the students, and in order to do that, he had put it into a real-world context, and the real-world context was baseball. I mean, there's a lot of physics in baseballs, right? Trajectories of balls, bats and balls colliding, runners running, you name it. You can do a lot of physics with just baseball. So in class, he would use examples from baseball. On the homework, he would put baseball problems. On the midterm examinations, he'd put baseball problems. At the end of the semester, he was writing the final exam, and he realized he had run out of baseball problems. So he decided to use football. Professor, complained the students, we've never done any football problems before. You're laughing. And I'm sure you recognize some of your own students. But think about it. If you're unable to transfer what you've learned into a new context, you have not really learned. And if education were just a transfer of information, then the teacher will set the bar because, the students can never rise above the level of the teacher. I want my teachers to stand on my shoulders. I want my students to stand on my shoulders. I want my students to solve the problems I have not yet solved. Right? We have lots of problems to solve. We want the next generation to solve the problems that this generation has not yet solved. Which means we have to really equip our students with the skills, with the problem-solving skills that allow them to tackle unsolved problems. From conflict resolution to energy, resources, water, you name it. Not only in science, across many different disciplines. Now, what's the result of this focus on the transfer of information? It took a while for me to discover it. It took actually until 1990. In 1990, I came across a survey called the Force Concept Inventory. How many of you know about the Force Concept Inventory? Can I see a show of hands? A few people. The Force Concept Inventory is a very simple survey, 29 questions. Well, the new one at 30. In 1990, had 29 questions, which tests students' understanding of the concept of force. Force is central in physics. You typically introduce that in week 2. And if you don't understand the concept of force as articulated by Newton's 3 laws, it's impossible to make sense of anything else, like momentum, work, energy, and so on. Well, let me give you an example of a type of question that you have on the Force Concept Inventory. A heavy truck and a light car collide head-on on the highway. The force exerted by the truck on the car is A, larger than that of the light car on the heavy truck during the collision. B, the two are equal to each other in magnitude. C, the light car exerts a larger force on the heavy truck than the other way around. D, I see a lot of people with their hand on the clicker. I'm not going to ask you, don't worry. D, they're not exerting any force on each other. They're just in each other's way. Many of you are laughing. You know, I think no physicist in his right mind could ever come up with such a crazy answer. See, and that's the problem with multiple choice tests. It's when you're the expert, it's easy to come up with the right answer, but it's very hard to come up with plausible wrong answer. Now, Professor David Hestenes, who developed this test, did not come up with these distractors. What he did was give the questions as open-ended responses and then tabulated the most frequent incorrect responses to construct this multiple choice test. This is why it's such a fantastic instrument that actually tests students' misconceptions. Now, most students who've taken physics can recite Newton's third law. You may have heard of it. Action is reaction, or the force of A on B is equal in magnitude to the force of B and A. They all know that. But if you replace A by heavy truck and B by light car, they forget all about Newton's law and they're convinced that the heavier object exerts a larger force on the lighter one than the other way around. I read that, I thought, no way. But then I saw some data that were really interesting. The data showed the following. It showed that if you give this test on the first day of class before students have had physics, and then you repeat it at the end of the semester, you get almost the same result. In other words, the students don't change their intuitive beliefs about how the world works, in spite of being able to solve textbook problems. I thought, no way. Not my students. Not Harvard students. But you know, I'm a scientist, so one of the things you learn is you better show the data. So it was too late to do the pretest. We were already dealing with rotational dynamics. We were way beyond Newton's third law. So one day I walked into class and I said, look, I'm going to give you a quiz. I didn't want to call it a test. You know how pre-meds are. You say the word test and they freak out, right? I'm going to give you a quiz, and you don't have to worry about this quiz because it's not going to affect your final grade in any way. I'm just giving it to test the effectiveness of my own teaching. As I said that, I realized I'd just taken away the incentive for them to participate. You know how pre-meds are, right? It's not only final grade, I don't show up. So I thought I'd better give them a reason for taking this test seriously. So I said, look, we have a midterm coming up in a few weeks. If you take this quiz seriously, it will help you pinpoint any conceptual difficulties you have with the material. As soon as I said that, I realized I told them a huge lie. I mean, the midterm exam dealt with, you know, moments of inertia, of complicated three-dimensional objects. I mean, it was way beyond Newton's laws, which we discussed in the first 2 weeks of class. So I was worried that the students would be offended by the simplicity of this test. Oh boy, were my worries quickly dispelled, because hardly had they started on the FCI or one student raised their hand, Professor Mazur, how should I answer these questions? According to what you taught us, or according to the way I usually think about these things? I had no idea how to answer that question. And by the time the test had been completed, I had been dragged out of my ivory tower. So let me show you the results. And I'm going to start with this post-test in 1990, which is the test that I was just describing. I was teaching a completely traditional class. So this was after teaching, right? There are 29 questions, and you can see that 2 students got full marks on the test. When I took the test, I got 28 out of 29. I must have misread a question or something. I actually made a real mistake. Anybody who scores below 23 is still partially an Aristotelian thinker rather than a Newtonian thinker, connecting force and velocity rather than force and acceleration. And as you can see at Harvard, after I taught them, some 70% of the students, or well, maybe not 70, 60% of the students are below that threshold of Newtonian thinker. If you take a gorilla, and you put the gorilla behind the keyboard pressing random keys, the gorilla will score about 10. As you see, we have some students who belong in the zoo at Harvard. So this is the post-test. In the years after that, I collected many pre-tests. The pre-test is very stable. It doesn't vary very much from year to year. So just for your interest, I'm going to show you the average of the pre-test from 91 and 94 so you can compare it. got some gorillas there too, right? And here's the post test that I just showed you. So you can see there is not much difference. That's what I got my 4 or 4.5 student evaluation for. They weren't even able to understand the concept of force taught in week 2. Yes, they were able to do textbook problems, but we'll talk about that in a minute. Let's plot this slightly differently. Let's take the average of the blue distribution, that's 70%. We put the initial class average on the horizontal. Then we take the red distribution, take the average, is 78%. And we put the gain, the change in the score, 78% minus 70% on the vertical. So we can combine this whole graph into one data point shown there. If you start at 70, you really want your students to be as close as possible to 100. Right? So the maximum gain, if you start at 70, is 30. For a perfect post-test score, you would be on this diagonal line, right? Start at 80, gain 20. Start at 20, gain 80. The reason I'm plotting it this way is because it allows me to compare to other institutions. So these data points shown here show other institutions teaching physics in a traditional, lecture format, from community colleges to large state school to a single Ivy League school. You can see the community college students start much lower, but they gain more. But there's a trend here. If you take all of these data points, regardless of the academic setting, the students only realize about a quarter of the maximum possible gain. Here, 8% instead of 30. There, 20 instead of about 80. Right? So all across the educational spectrum, the lecture method is not very effective. So clearly, my students had not yet assimilated the information. Yes, they were able to parrot it back. In fact, after I saw this test result in 1990, for a while I thought, wow, maybe, Eric, you're not such a good teacher after all. But that could obviously not be true, right? So I disregarded that right away. So as I tried to explain this result to myself, I thought, well, maybe I have dumb students. But in my institution, it's kind of hard to claim. So I thought about it some more, and then my twisted brain came up with the perfect excuse. Put yourself in my position. I'm telling you this just to show you how I struggled with this result. So put yourself in my position. You see this graph here, right? And how do you explain that to yourself? Oops, this one. No, because after all, they did well on exams, and they gave me high ratings. They don't care. No, I had a much better explanation. They cheated? No. Testing the wrong thing. A bad test. Think about the heavy car and the light truck, right? Maybe it was just a matter of semantics. So I decided to do some testing of my own. I wish I had time to show you the data because they're hilarious. But I compared the word-based problems in electricity and circuits, basically, electric circuits, with a standard textbook problem. I gave it on a midterm examination, no multiple choice, nothing, just the two, word-based and just a textbook problem. The students were able to do the textbook problem flawlessly, but they were unable to do the word-based problem because they simply were applying rote problem solving to the problem. They categorized the circuit problem as a circuit problem, looked for the right equation, plugged the numbers in, turned the crank, and out came the right number. But if the circuit problem was hidden in words and diagrams using light bulbs rather than the textbook illustration of a circuit, they were unable to see that the same principles applied. So it's not the transfer of information that is important, it's this assimilation of information that is important. So if we stop to think about this for a moment, and we say education is a two-step process. One, you transfer the information. We have to have transfer of information, right? Without transfer of information, we can't even start. Let's be sure, 100% of us should agree on that, right? The transfer of information is essential. No transfer of information, no education. But, as 98% of you said, there's a second step. You need to do something with that information. Not just memorize it or write it down in your notebook. You need to actually have an aha moment. Oh, I get it now. Where did that aha moment occur for you and for me. I've often thought about it. Did the aha moment, the sense making, did it happen while you were sitting in your chairs listening to your professors? Maybe a few, most of them, I would say, happened outside of class. And if we ask ourselves, which is the important part? Is it one or two? I think we'd all agree it's probably two, right? In the standard approach to teaching, this happens in class, and that happens outside of class. And it happened for you and me outside of class without us actually noticing. We became successful, we became professors. It's unreasonable to assume that all of our students who are going to have very different careers, that's going to happen at the same rate as it did for us. That's okay. I travel too much, never can back up my computer. Okay, so really, we should really be focusing on this step. That's the easy step. This is the hard step. So why don't we take this and invert it? We put 1 out of class and 2 in the class. So what I decided to do was to move the information transfer out of class. And now I have my students either read the book or my notes before coming to class, or watch the class online before, because I videotape all my class anyway, so why not just watch it? Why? If you stop to think of it, we have such an inefficient enterprise reenacting the same lectures over and over and over and over again. And yes, if there was a real interaction, then it would be meaningless to film it and put it online because you couldn't follow the interaction, right? However, that's not the case. So why not just videotape it, put it online? And you can either watch it online or you can read the book. And in fact, there's right now is this whole flipped class. There's a lot of emphasis, but unfortunately, everybody focuses on this first part. I think we should really focus on this second part. What is it that we're going to do in the class if we do this? And that was sort of an accidental discovery. After realizing, oh, Eric, you're actually not a good teacher, the first thing that came up in my mind was, well, maybe I should only teach graduate courses. But then the solution presented itself serendipitously. All the great things in my life happened serendipitously. In fact, this afternoon I'll be talking about black silicon, which is another story of serendipity. I told you a moment ago that I was worried that my students would be offended by the simplicity of this FCI. They were not offended at all. They were horrified. And they asked me to organize a special session where we would go through every single question. So I booked a classroom in the Science Center at Harvard for 3 hours. We went through every single question. When we got to this question of the heavy truck and the light car, I drew a sketch of the heavy truck on one side, light car on the other. I drew the forces of gravity, all the forces in there. And then I said, by Newton's third law, the force of the truck on the car is equal to that of the car on the truck. What more is there to explain about it, right? I turned around and I could see from the faces of my students that they were confused. So I asked if there was a question. They were so confused they could not articulate the question. You know how it is, right? If you read it. So I thought, this is serious. So I erased the board and I thought I start over again. And I thought maybe they're confused by the fact that, yeah, the forces are the same, but the effects are different. But that's because the truck is so much heavier than the car. So I thought what I should really do is bring in Newton's second law. Anyway, for 8 minutes, I gave the most brilliant explanation, connecting Newton's third law to the second law and the acceleration. The board was just covered with equations. And then I turned around, jacket covered in chalk dust. I was triumphant, only to see that they were even more confused. And they could still not articulate a coherent question. I knew, however, that 50% of them had given the right answer on the FCI test. So in a moment of despair, I said, why don't you discuss it with each other? And something happened that I had never seen before. The entire classroom, 250 students, erupted in chaos. They forgot about me in front of the classroom. Normally I would lecture and then I would stop and say, does anybody have a question? Anybody? And you know how it is. The students look down. They don't want to make eye contact, right? Nothing. If you wait long enough, it's always the same person in front row reluctantly raises his or her hand. But, you know, most of the students do not want to interact in the classroom because they're put in a passive. Let's think about the learning space for a moment, right? Why? This dates back to what? The amphitheater, the Greek amphitheater, 2,000 years ago. Why did the Greek develop the amphitheater? To teach? No. For performances. Entertainment, exactly. To focus the attention of many on a few or one. Right? And it's the performer who is at the center of attention, who is active, whereas the audience is passive. If you look at an illustration of the School of Athens, you don't see students sitting in an amphitheater. They walk around in pairs and talk. Peer instruction is very old. There's nothing to do with Eric Mazur. It's, you know, Socrates, basically. But somehow we adopted this, and this architecture puts you in a passive role right away. As soon as you sit down, you expect something to come to you, not to come back from you to the presenter or the performer or whatever. Anyway, so there they were all engaged, talking one another. And the biggest miracle was, in 2 minutes, they figured it out. I had, for 10 minutes, unsuccessfully tried to explain it. In 2 minutes, they figured it out. Imagine you have two students sitting next to each other, Mary and John. Mary has the right answer because she understands it. John does not. On average, Mary is more likely to convince John than the other way around, simply the force of logic, right? But, and I think this is the most important part, Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because she has only recently learned it. She still knows what the difficulties are that the beginning learner has. Whereas Professor Mazur has learned it such a long time ago. To him, it's so clear that he cannot even understand why somebody doesn't understand it. It's what Steven Pinker calls the curse of knowledge. It's sort of an ironic statement, right? Because you think the more of an expert you are, the better qualified you are to teaching. But I actually think that the more qualified you are, the harder it becomes to teach, because you forget how you learned it, and you forget what the difficulties are that the beginning learner has. And I'm sure that resonates with you, both as a student and as a teacher. As a teacher, you may have had students come to you, ask you a question, and you look at the student and you think, what's going on in the student's mind, right? You can't connect somehow. You have no idea what the question even is about. As a student, you probably have had occasions where you wouldn't even bother asking the professor because you knew you'd get an answer that goes straight over your head. Here, we're basically multitasking, all the students talking together. So I teach now by questioning rather than by telling. I come into the classroom, I talk a few minutes, I put a question on the board. Students think about the question. It's silent. There is actual time to think in the classroom. After that, I make them commit to an answer by polling. Before we had clickers, we did that with flashcards, or it was a show of hands. I had them basically put their fingers on their chest. 1, 2, 3, 4, 5. Then I tell them, find a neighbor who has a different answer and try to convince that neighbor. Poll them again, usually with far more correct answers than before. Then I either have the students explain it or I explain it myself, and we repeat the cycle till the time is up. And of course, the learning, the aha moments occur in this discussion. It's actually fantastic. You tell students to talk to each other, you have this chaos, and you'll actually see students go, oh, yeah, it's so gratifying. Even if you close your eyes, you can hear the aha moments occur. Let me show you a little videotape of how this works in practice.
So we have a rectangular loop that is placed in a uniform magnetic field.
Don't worry about the question, okay? I'm not going to poll
The
you.
question is,
I read the question with them so they understand what the question is about.
this loop. So take a minute to think about this and then enter your answers.
They think. I give them more time than is shown on this tape. I can see on my screen what they answer. I do not show them this distribution.
Disagreement clearly here.
So they don't see this.
So turn to your neighbor and see if you can convince one another of the correct choice.
It goes out, in, right. There is a fork. There is a fork. How do you know that? I said, what did you say? It has to be a fork.
Initially, we had sort of an even split, and now we have absolutely overwhelming majority for choice number 2. So
They do see that second distribution, not the first one, but they do see the second one. So what's going on here? One, it's active, not passive, like the lecture format, right? It's active. You cannot sleep through my classes, because every few minutes your neighbor will start talking to you. Secondly, now there's a two-way flow of information, and not just information from me to the students, there's information coming back. If they don't get it, I see it on my screen, then and there. I don't have to wait till the homework, or the midterm exam, or the final exam. I can still do something about it. Furthermore, it's an opportunity for students to assess their own knowledge. It's not a problem if they get the wrong answer, right? That's okay. But in the second distribution, they can see where they stand relative to their peers. And if you're in the 10% who still gets it wrong after the discussion, you go, uh-oh, I better look at this. Points are not necessary, right? You just get the feedback on your learning. So, you want to try it? Yeah? Okay. Yes? Question.
I can see how this would work really well with disciplines where there's one right answer and 4 wrong answers.
Yeah.
But I teach in the humanities,
Yeah.
and it's more about ideas and, different opinions are coming up. And I can sort of see how I could do this in a class, but I'm curious about what your perspective on, let's say, how this would work in an English class or a theology class.
So the question is, I can see how this works in a classroom where there are questions that have right or wrong answers, like science. We like to think that there are right and wrong answers, but it turns out it's actually a little bit more subtle than that. But anyway, I understand completely what your question is. The person who was asking me the question is teaching in the humanities departments, where there are things like opinions, interpretations, and so on. So how could you use this method in there? Did you sign up for the workshop this afternoon? I'm going to actually do a humanities question. Okay. So the answer is yes. Anything that has an interpretation, anything that is not fact recall or memorization. For example, let's say that you're looking at a work of art, right? We can no longer consult the artist. It might be long dead. And there might be an interpretation from different scholars and even contradictory interpretations. You could, as a teacher, just say, this is the interpretation of this work of art. Or you could say, here are different interpretations. Which one do you believe is the correct one? And in that case, there is not a correct or a wrong choice, but still, you want your students to be able to make their own interpretations, and you can start a discussion. So I teach a course on ethics, which is the same thing. On the extremes, you have right and wrong, but in between, there's a big gray area where people can argue forever and not reach agreement. So what I do is I present the little case or the work of art or whatever, and I have people make a choice. Then I show the distribution and ask a few people to articulate why they made that choice. Then I have them talk to each other, try to convince, and you'll see the same aha. Oh, I had not thought about this. Yeah, I like your interpretation more than mine. And you can see a shift. And people learn a very important skill. They learn not to accept your interpretation or the interpretation of the scholar, but to make their own interpretation, to voice their own opinion. So important, right? So I think as long as you don't just teach fact recall or memorization, and I think none of us really wants that, right? Then this method empowers the students to use their own brains. And it's much more broadly applicable. You'll hear me use the word right and wrong, but they're not essential. Thank you for asking our class. And I'm planning, for those of you who come to the workshop this afternoon, on actually demonstrating that. Okay, you want to try it? Yeah? So I'd asked the Center for Teaching and Learning to distribute a little handout on thermal expansion. Did you all read that? No? What are you laughing about? This method doesn't work if you don't read beforehand. I'm just kidding. But you know what that means. That means that I will have to lecture you on... Actually, I'm very grateful because the one thing I regret about peer instruction is that I don't get to lecture anymore. So thank you for giving me the opportunity. So I'm going to ask you a question on thermal expansion. Let me tell you a little about thermal expansion. Solids, and metals in particular, expand when they get hotter, get bigger in volume. Very important. This is a picture of a railroad in India that was incorrectly laid down. You can imagine what happens when a train goes over that. You may have been in a train and noticed when the train goes at low speed, why you hear this clickety-clack sound of the wheels. It's because the different sections of the railroad from which it's made are not jammed together, but there's a little gap there. The gap is there to allow for the expansion. Important problem in engineering, not only for railroads, but also for steel beam buildings where the metal expands at a certain rate that's bigger than the expansion of the plaster. You don't want things to break and fall down. So, major problem in engineering. Also, many applications from thermostats to other is important. You may wonder, why is it that materials and metals in particular expand? The reason is that materials are made out of atoms. I'm showing 9 of them here. And when atoms get hotter, they get further away from one another. So this is cold, and this is hot. Cold, hot. Okay? That's it. That's all I'm going to test. Now, 2 things. You may wonder, why is it that atoms get further away from one another? The reason is that what we call temperature has to do with the motion of atoms. Atoms don't sit still, they vibrate. And the amplitude of the vibration is what we perceive as temperature. So these are cold atoms, and these are hot atoms, right? And simply by virtue of moving over a bigger amplitude, you need more space, right? So they all push each other aside by having a bigger amplitude. When you put your hand on something and you feel the temperature, you basically feel that energy associated with that motion. But, I'm not going to ask you that, so don't worry. The real thing is this. Questions, anybody? It's not just those 9 atoms, really. It's all of them, the millions of billions of atoms. They all get further away. Any questions? Look, I'm not going to... See, what I could do is I could make the screen black and then ask you a question. When metals get hotter, they expand because A, the atoms get closer together. B, they stay the same distance. C, they get further apart. But that would be just me giving you information and then you giving the information back to me. I'm going to take this picture of the atoms getting further apart from each other, all of them, and put it in a new context. So you better be sure that you understand it. I knew I gave brilliant lectures, So no questions at all? Yes, thank you. What about the one in the middle? Very good perception. Look at that, it doesn't move. But look, I could have, that's just because of the way I put the 2 pictures on top of one another. I could have put this one on top of that. What would have happened to this one then? It would have gone down. And this one would have gone twice as far. And this one, instead of going up and to the right, would have gone to the right. The key point is not so much where they end up in an absolute sense. The key point is that they all get further away from one another. Right? This from that, that from that, that from that, this from that. They all get further away from one another. And I happen to have put the 2 pictures in such a way that this atom is on top, but if I had pegged that atom on top of the previous one, they would still have all gotten further away from one another, but it would have been this one that would have moved. So the point is not so much how much they move with respect to their original position. No, the key point is they get further away from one another. Thank you for that question. Yeah.
But when you said that right now they're getting closer together.
Which ones?
Light gray ones.
Here, these 2, the gray ones are the hotter ones, right? These are now cold, they're close together. Oops, wrong way. And now they're further away from each other. Right? It has moved further away.
Okay. So
Further away. Further.
Is the original position.
The gray is the original position, Yeah.
Why do some solids expand further with the same increase in temperature?
Yeah, so different solids have different coefficients of expansion, they're called. So some materials expand more for a 1 degree increase in temperature than others. But it's pretty linear. So in other words, if you increase the temperature by 1 degree, fraction of a percent. If you agree another degree, same amount in fractional increase. But let's say copper will have a very different expansion coefficient from aluminum. And metals have a much larger expansion coefficient than plaster or glass or wood or anything else. You're way beyond what I'm going to ask. Yes? Are there other events that would cause similar kinds of expansion? Yes, the pressure at some point also matters. You could take a metal and compress it a little bit, or you could do the opposite. Well, we're already at pretty low pressure, but if you increase the pressure, you can squeeze materials together.
So when you heat them, they expand, and when you cool them, they contract.
Yes, so when you heat them, right? So if you take this metal, we heat it, it expands. When you cool it back down, it contracts again. It's reversible. Completely right. Okay, I think you're way beyond. Are you ready for the question? Yeah. Okay. Where's my remote control? So here we go. Remember, no talking to each other. If you talk to each other before I tell you to talk to each other, I'm going to come to you and put the microphone in your face. Okay? After you've talked about it and you've answered, ask yourself, how am I going to convince this person next to me that my answer is right? Now, when I ask you to talk to each other, you have to find somebody who has a different answer. If you talk to somebody and has the same answer, you say, thank you very much, and you turn the other direction. If everybody around you has the same answer, get up and walk around, okay? Once you've convinced somebody, don't just sit there, because if you sit there, I'm going to come and talk to you. Try to find another person. It continues, okay? Instructions clear? Okay. So, consider a rectangular metal plate with a circular hole in it. You can feel the question coming, huh? When the plate is uniformly heated, the diameter of the hole, 1, increases. Look at that, 2 people have already responded. Think before you answer, please. They're from the... Okay, so when the plate is uniformly heated, the diameter of the hole, 1, increases, 2 stays the same, 3 decreases. I'll give you a minute to think about it and to connect that to the idea of atoms getting further away from one another, all of them. You'll get to talk to each other in a second. God, there's some people whispering there. Okay, 30 more seconds left. Make it a game. If by now you have no idea, just, pick a button between 1 and 3. But do commit yourself. I want you to commit yourself. Okay, so why don't you check out with your neighbors what they have, and remember, talk only to a neighbor who has a different answer. Go ahead. Hello? Hello? Look at this. I can't even get your attention back. Look, and they continue there. It's okay. It's not going to affect your final grade. Look at how incredibly engaged you are. I'm sure that by now you have forgotten that I'm here to talk about education, not about thermal expansion. I mean, it's amazing how engaged you all got. And I can still see some people sit there in the back go. It was making sketches and so on. Imagine I just given my little lecture about thermal expansion and then told you, let's now apply this to rectangular plates with circular holes in it. If you take one of these plates and put them in the oven, the diameter of the hole will... I'm going to keep you in suspense a little bit longer here. Would you have had the same level of engagement? You would have probably just taken down some notes and written them down, but you would have not had that opportunity to think about it and that level of engagement, forgetting about me in front of the classroom. So before I tell you the answer, let's analyze what happened here, right? One you made a commitment. I had you press a button to make a commitment. After that, I asked you to turn to your neighbor and you externalized your answer. And what happened there was really interesting because all of a sudden, the discussions were no longer about the answer. They were about why. I could see from the sketches you made, about the atoms moving and so on. You were trying to articulate the reasons behind the answer. It was no longer the outcome that was important, it was the process. And in real problem solving, that's exactly what is important. It's not the outcome. You know the outcome. Right? Imagine you're working in the banking sector, you want to make investments. You know exactly what the outcome you want. More money in the end. The question is, how do you get there? Any problem we have follows that pattern. Known outcome, unknown process. You are actually starting to focus on the process rather than on just the answer. So you moved from fact or from answer to reasoning, and you had an opportunity to sharpen your reasoning skills. But more importantly, you became emotionally invested in this. If I were to walk out of those doors now, you'd come running after me, asking me what the answer is. The answer doesn't matter. We're talking about education here. Anyway, I want you to answer this again, a second time. What you now believe to be the right answer, before I reveal the answer. So please enter what you now believe to be the correct answer. And the choices here. Here we go. Here are the choices. Thank you for reminding me. So I thought that my lecture was pretty darn clear. And you agreed, because I had to work really hard to get any questions out of you. Unfortunately, I have some bad news. Only 25% of you got the right answer the first time. Now, the method requires there to be at least 35% correct answers before. If you have 25% correct answers, there's just not enough people. That means that only one in every group of 4 people on average had the correct answer. So I'm not very confident that it will have worked in this case, but you made the 2 important points that I wanted to be made. 1, lecturing sucks. 2, you got so engaged by this thing, which is really not that interesting, that you're not going to let me leave until I tell you the answer. The correct answer, look at that. It's just fantastic when you got an audience that's so hooked. And believe me, students are exactly like that. You don't need to give them points. There's something about the human mind wanting to understand, wanting to get it right. Just look at any children, right? They're sponges. They keep asking why. And then in our educational approach, we manage to erase that curiosity. Here, I brought it back. And you can bring it back in your own classroom. It's not that hard. Because we want to be independent thinkers. We want to formulate our own understanding. Okay, so the correct answer is, drum roll, number 1. Oh. Look at that!
Yeah, you said that again. You said it.
I put the 2 distributions here next to each other. You did better the first time. I challenged you a little bit too much, and I gave a loud hello. It's okay. It's okay. Look, I don't want you to lie in bed tonight. So let me spend a precious 2 minutes here trying to explain it. Imagine you have a jar. It's okay. I'll try it. Imagine you have a jar of marmalade in the refrigerator. Glass jar, metal lid. The lid consists of a ring and a metal plate. You take it out of the refrigerator, you can't open it. What do? You run the metal lid under hot water because the ring will expand and it's easier to open. You say, that's unfair. This is a metal plate. That's a ring. Okay. Imagine we have a metal plate. Do I have a metal plate here? No. I don't have it. Yeah, I can use this. Right? With no hole in it. No hole in it. This is my metal plate. I draw a circle on it. There's no hole. I just draw a circle on it. Now I put this plate in the oven, and the plate expands. What happens to the diameter of the circle? It's bigger. You say, yeah, but that's because there was no hole. If there was a hole, then the atoms would expand into the hole in order to get further away from their neighbors. But let's think about this. Let's consider for a moment. I can't get this back in my pocket here. Let's imagine the atoms at the edge of the hole. It's not too cold outside. It's a beautiful day. We could go all outside, form a large circle. We are the atoms at the edge of the hole. Now we all step inside towards the center of the hole. What happened to the distance between us? Can't, right? Our neighbor is shaking more, needs more space. The only way to get further away from one another is to step out. The only way would be to remove some atoms. But you know, the atoms are all bound to each other, so they can't just move around. You won't forget this. Okay, back to PI, right? I'm not here to talk about thermal motion. 2 points. One is, you see how hard it is to assimilate information in just a quick lecture, right? There was just no time for you to process the information about the atoms getting further away from each other, right? Had you done your reading as I requested, I'm just kidding. The other thing is, notice the level of engagement, right? The desire to learn, the desire to understand. Back to peer instruction. I'll get to questions in just a minute. Well, no, go ahead.
So I had the aha moment before you gave us the real answer. I thought it was 3, and then it became 1 for me. It made sense because of that. But why, if there's space in the middle, don't the atoms move toward the open space?
Let's discuss that later, right? But thank you very much for making that point, because, you know, notice the engagement. I get letters after my discussions asking me to explain this question via email. So I will make myself available in the break, okay? But let's focus on education here right now, rather than physics. So we've shown here that sometimes the number of correct answers can even go down, right? What about the long term? Usually it goes up, and I'll show some data in the workshop later on. But let's do the FCI again, the first year that I implemented peer instruction. Now, you know, scientists, I've noticed this from going to many physics conferences. You know, sometimes you see physicists pop up a chart with data and say, let me show you some typical data. I've learned that the word typical is a code word. It means here are the best possible data I've ever obtained in my entire career. I'm going to show you the worst data I obtained with PI the first year when I didn't know what were the right questions for my physics students. Here's the pretest from 1991. Here's the post-test. Yes, we still have some students who don't understand Newtonian mechanics, but it's a much smaller fraction. And we certainly eliminated the private section of the classroom here. And if we put the two distributions together, you can see that we have actually moved the distribution significantly up. You know, I was so excited when I saw these data. I thought I have to talk about this. So I submitted an abstract to the American Physics Association of Physics Teachers, who held their annual meeting in Vancouver that year. Nobody knew about me in education, so all I got was a 8-minute contributed talk. I flew out to Vancouver, and I thought, I don't want to be accused of having taught to the test. I never, in my classroom, never used a question similar to the FCI. So I spent 4 of my precious 8 minutes documenting that I had not taught to the test. At the end of my class, somebody raised his hand in the back and said, don't worry about teaching to the test. We've tried it. It doesn't work. These preconceptions are so ingrained that, you know, even if you teach to the test, it doesn't help. So let's go back to this plot. Instead of an 8% gain, we have a 16% gain. And in the year since, that data point has moved up by selecting better questions for in class. And the highest data point, this one, was obtained by 2 of my colleagues when I was on sabbatical. So Not even to do. Other institutions that have implemented the same method have seen similar gains. And if you take not just the best data, but all the data, you see that implementing interactive teaching doubles the gain on the FCI. But the FCI is just a small part of the curriculum. I knew my colleagues would ask me this question: what about problem solving? How do you do that? How do you test that? I knew of only one way: repeat an old exam. I had never ever repeated a single exam, but I had kept meticulous data, and I was able to reconstruct this histogram for an exam I administered in 1985. I said to myself, look, as long as the average remains near 62, I'm happy. I was worried it would actually go down a little bit. Why? Because in 1991, I decided that solving problems in front of students was not the right way to teach physics. And before that, I would always have example problem solving. With my back to them, writing the solution on the board. But think about it. If you want to learn to play the piano, you don't just go to the concert hall, listen to Murray Pariah playing the piano. You got to do the playing. Likewise, if you train for a marathon, you don't go sit in front of the TV eating popcorn, watching marathon runners. You got to do the running. And to learn physics problem solving, you don't just watch a Harvard professor solve physics problems, you got to do it yourself. So we did the problem solving outside of the class for the students on their own, not in class. Provided help, of course, but just a sample problem, the only thing that would happen is that the solution would end up in the notebooks of the students. Actually, I once heard somebody describe the lecture as a process whereby the lecture notes of the instructor get transferred to the notebooks of the students without passing through the brains of either. Anyway, I gave the same exam, and you know what? The students did better. Statistically significantly better. Here are the two distributions. So what does that mean? That means that better understanding leads to better problem solving. Duh. Isn't that obvious? If you think about it, that makes actually a lot of sense, right? But, and this is the most important message I want to get to you today, good problem solving doesn't always mean understanding. I'd been fooled into believing I was a good teacher for many, many years, simply because my students were able to solve textbook problems. But they were doing it by rote. It was a house of cards. So I promised you some data about the lecture, and this will be my last slide. What happens in a lecture? In a lecture, students do not pay utmost attention. You had not yet chance to assimilate this information about the atoms getting further apart and build a mental model that allowed you to apply this to a new context. But another thing is that in a lecture, your mind is held captive. And at the MIT Media Lab, they did something pretty stunning. This was not actually a study in education. This was a study about a sensor that they developed. But there's a graph that sheds a lot of light. And we're now collaborating with this group of Ross Picard to get more actual data. They developed a little wearable sensor that you can wear around your wrist like a watch. And it measures electrodermal activity. Electrodermal activity basically measures neurological activity in the wrist, which they show in this paper is very strongly correlated with brain activity. Not that surprising because the neurons are connected to each other, the nerves all the way to the brain. So they can use this as a proxy for brain activity. This means you can give a student one of these sensors and have the student walk around for a week and monitor brain activity for a week. Right? I mean, you could, of course, do an EEG, but I think not many people want to walk around with electrodes on their head. Well, MIT students perhaps, but and then they downloaded the data, and here is a week worth of data for the students. For one student, sorry. So day 1, day 2, day 3, day 4, day 5, and so on. On the horizontal is time, starts at 4 o'clock. I don't know why the time starts at 4 o'clock at MIT, but anyway, 4 o'clock to 3 o'clock. And they asked the students to keep track of the activities they were engaged in. That's written in the small letters underneath, which you might not be able to read. That's okay. I want you to see so you can see, lots of brain activity, less brain activity. Look at the parts that are labeled class. The trace goes flat. Compare that to sleep, this highlighted region. The brains are very active during sleep. And we know that because, you have REM sleep. Information gets transferred from short-term memory to long-term memory. Right? So, yes, actually, the students their brains are more active when they're asleep in their bed than when they're asleep in the lecture. Now, don't look at the graph. Look at me. Okay? Don't look at the graph because I'm going to ask you a question. And the answer is on the graph. So don't look at it. There's one activity that matches lecture in lack of brain. What is that? TV. Watching TV. There you go. The trace goes completely flat. And people had known that for a long time because back in the 70s they did EEGs of people watching TV and they noticed that you go into a meditative state with mostly alpha waves and no beta, gamma, and delta waves. Yes?
Have they put those sensors on instructors?
No. So we're actually doing that. We're actually doing that in my class. But there's a lot of, if you look at study, if you look even at chores, if you look at any social activity, let's see, of course this is MIT, so there might not be that much social activity. God, day 3? Social. You see, there is more activity there than in class. So I think the act of speaking is actually cognitively a much bigger load than listening. So, but we're doing that. Yeah, we're doing that. What was I going to say? Oh yes, I mean you may have seen a movie of a book you've watched. Right? Read a book and then later seen the movie. And I think most people, I'd be surprised if you're different, enjoy the book more than the movie. And the reason is actually the same, is that when you read the book, you're using your brain to imagine things that cannot be depicted by just words. And you can stop, you can pause, right? I mean, you don't read non-stop. You read, you put the book down, you think, you imagine. So your brain is actually active in filling on all the missing pieces and building, a visual imagination, if you want, of the book. When you go to see the movie, there is no time for that. The information is just coming at you, coming, and the brain has no time to think. There might be emotions, but there's no imagination. The imagination has been done for you, right? So I think it's the same thing with a lecture. And we should not be surprised that the lecture is not better than TV. And this also tells you a lot about online learning, right? If we just put it online and it's just a videotape of a lecture, it's not in and of itself going to be much better. We need to provide opportunities for students to stop and think and answer questions. So the other thing is, you think you know it. You thought you knew it about the atoms. But the reason is you had not yet been confronted with any misconceptions. You had not even had time to think about it. I gave you no time. So you walk out of this lecture with a completely false sense of security. I have it so often. On Fridays we have our colloquium. I'm missing it today because I'm here. Usually we have professors from Yale, Stanford, Berkeley, and so on giving talks about their work in nanophotonics. I go, brilliant presentations. A few hours later, I'm in the hallway. Colleagues come to me. Oh, did you go to this talk by the professor at Stanford? I say, yeah, I went. How was it? It was fantastic. I want to make my colleague feel bad about not having attended the talk. Really? What did he talk about? And that's when you realize, yeah, it all sounded good, but to reproduce it, I don't know how to do it. So in the end, it's really all an illusion. And I think I hope I've convinced you a little bit that education is not just about transferring information. It's not about getting students to do what we do. We must have active participation. Now you have this technology that we use, but it's not necessary. I can show you this afternoon how to do it without any technology. And incidentally, we do want you to leave those little clickers behind. They don't control your microwave or your television. So. But I think this tweet sort of illustrates how technology can be used incorrectly. From Marshmallow, this was posted a few months ago on Twitter. Dear Professor, you force us to come to class for clicker points, but no one pays attention after because the notes are online. Can I go home? So here's a professor who uses the clickers just to get points, to take attendance in a sense. That's not going to get students to learn more. It's not their bodies that we want in the classroom. It's their minds that we want in the classroom. Thank you very much. If you want more information, here's the URL.